Hello everyone, welcome. Just before I get started, can everyone hear me? Just put a quick message in the chat box if you can hear me. Great, thank you. Welcome everyone. So before I get started, I'd just like to ask you all to turn off your notification settings if you haven't already. You can do that by going to your settings or the cog symbol. It should be in the bottom right hand corner of your screen if you're on desktop. And just untick all the notification settings so those can be a little bit disturbing while you're trying to watch the webinar today. So today's technical webinar is Greener and Better Concrete with Supplementary Materials. It's being presented by Dr. Shasha Wang, who is a lecturer in our civil engineering school, and she's based in our Melbourne campus. Now, I'd just like to say, if you're new to these webinars, this is actually the last webinar of the year. So it's been an incredible year so far, and we've had many technical webinars, and I think we're going to be finishing off on a good note today. And just some common questions. So everyone will receive a copy of the slides and the video recording via email within the next 2 business days via email. And we also provide a free digital certificate of attendance for live attendees for these webinars. So I'll provide a short link or QR code at the end of this session, in which you'll be able to request one. There's a short survey there for you to fill out. So if you're new to EIT, just to give you a brief overview, so we're an engineering specialist education provider. So we have a range of courses only in engineering. We offer courses such as professional certificates, which are our short courses. We have diplomas and advanced diplomas in the vocational sector. We have undergraduate and graduate certificates, bachelor's and master's degrees, and a Doctor of Engineering in the higher education space. We have industry-oriented programs, so that means our programs are regularly updated to stay relevant with the industry and rapidly changing technology. We also, our vocational programs and higher education degrees are registered and accredited by the Australian government. In addition to that, we have a range of qualifications that are also recognised internationally under one of the 3 international engineering accords, so the Sydney, the Dublin and the Washington Accord. We have industry experienced lecturers, so not only those who are involved in academia, but we have lecturers from all around the globe who have experience that they can apply to their teaching, which makes for a better learning experience for our students. We have a unique delivery model, which includes the use of these live and interactive webinars similar to the one you're in today. However, we promote small class sizes if you're a student with us. I mentioned our international pool of expert lecturers. We have dedicated learning support officers, so those staff, they assist you from when you start studying with us right to when you complete your course or you graduate. And we have state-of-the-art technologies such as hands-on workshops, remote laboratories, and simulation software. I'll now pass over to Dr. Shasha Wang, who will be delivering this technical webinar for you all today. Thanks, Shasha.
Thank you, Riley. Hi everyone. Please bear with me. I'm going to share my screen. Okay, let me try to move my slides. Looks like it works. Yeah. So I start the webinar today. Hello everyone. Thank you for joining with me for this technical webinar by Engineering Institute of Technology, EIT. I'm Dr. Sasha Wang, a civil engineering lecturer here at EIT. And over the years, I have been working on cement-based materials, behavior of high-performance concrete against severe loading conditions, and I'm also very interested in green concrete and low carbon concrete structures, and that's why I'm here today to share with you some information about green concrete from the perspective of using supplementary materials, especially supplementary cementitious materials. So this is the agenda item for today. Firstly, we'll be looking at why there is a need for us to make greener and better concrete using supplementary cementitious materials. And next, I will try to explain what are supplementary cementitious materials, and then introducing some of the most commonly used supplementary cementitious materials. And then how do we actually use supplementary cementitious material in concrete, followed by what are the benefits of using supplementary cementitious materials in terms of the cost, performance, and the environmental impact. And finally, I will share with you some new trends people are working on to make concrete more environmental friendly and with better performance. Let me start with addressing the first question: why do we need to use supplementary cementitious materials? Are there any other approaches to make concrete greener and better? Well, to answer this question, I need to start with global warming and carbon dioxide emissions. Global warming is the unusual rapid increase in Earth's average surface temperature over the past century, primarily due to the greenhouse gases released by people burning fossil fuels. Despite ups and downs from year to year, global average surface temperature is rising. By the beginning of the 21st century, Earth temperature was roughly 0.5 degrees Celsius above the long-term average between 1950 and 1980. Model simulations by the Intergovernmental Panel on Climate Change estimates that Earth will warm between 2 to 6 degrees Celsius over the next century, depending on how fast carbon dioxide emissions grow. Now we know that the December 2015 Paris Agreement's objective to limit the rise in global temperature this century to less than 2 degrees Celsius above pre-industrial levels. For this level of global warming, there is this is the amount of the greenhouse gases that can be spent. Then with the average carbon dioxide emission rate of about 1,337 tons per second, there is only approximately, we can see that only about 24 years before we will deplete the carbon dioxide budget. So we can see there is an urgency for us to reduce the carbon dioxide emissions to meet the goal of the Paris Agreement. This chart shows growth rate of carbon dioxide emissions of different countries last year. A positive figure indicates that emissions were higher than the previous year, and a negative figure indicates that they were lower than the year before. We can see that Australia and a few other countries are doing a good job with reduced carbon emissions from fossil fuels and industry last year. However, majority of countries over the world are still producing more carbon dioxide emission last year. Well, carbon dioxide emissions associated with energy and industrial production can come from a range of fuel types. The contribution of each of these sources has changed significantly through the time and still shows large differences by regions. In this chart, we can see the absolute contribution of carbon dioxide emissions by different sources. For example, coal and oil, gas, and cement production. The unit of this y-axis here is gigaton of carbon per year. We can see from this chart that in the present day, solid and liquid fuel still dominates, although contribution from gas production are also notable. Cement at the global level actually remains comparatively small, but the emissions due to cement is still about approaching about 0.5 gigatons per year. And then there is also data, we also have some data showing that construction sector actually represents about 38% of the world's global carbon dioxide emissions, and of which 30% are linked to building materials. Well, now at this point, let me ask you actually a simple question. Do you know what material is the most widely used construction material in the world? AC? Cement? Yeah, thank you. Steel? Wow. Cement? Okay, thank you, thank you. Well, thank you. So actually, cement, of course, concrete made by cement is the most used material in the world. It's not only for construction. When we are looking at the high carbon emissions, as we saw from the previous slides, because of cement and concrete, it would actually easily lead to the perception that concrete is not a green material. Actually, this is not true. Okay, I'd say concrete itself is almost the most environmental friendly construction material in the world. Okay, apart from the longer service life, less repair requirements, and the recyclable advantages, concrete also has a low carbon footprint on a unit weight base. Okay, if you look at this figure on the right, okay, it actually shows the embodied carbon dioxide and embodied energy per kg of many construction materials. The embodied carbon dioxide is the total amount of carbon dioxide produced in the extraction and the transportation of raw materials and also the manufacturing into final products. Sorry, final products. The embodied energy is the sum of all energy consumption, which includes the energy used for material exploitation, production, construction, installation, maintenance, and demolition. Okay, as we can see from this figure, both the embodied carbon dioxide and the embodied energy of concrete, okay, is actually much lower than many of the other construction materials here. Okay, let's say if you look at say timber, okay, timber, which is deemed as a green material, actually represents a much higher embodied carbon dioxide and the embodied energy per kg. Okay, but now why people are still so concerned about carbon dioxide emissions by concrete? Why? Because we use a lot of concrete. Okay, so concrete is the fundamental building material for infrastructures, office buildings, and homes. Buildings use concrete for their, including foundations, walls, columns, and floors. Highways and bridges are also built with concrete. Airports and railway stations use concrete as well. Our drinking water system is also delivered through concrete pipes from treatment plant made with concrete. Concrete structure is actually structures are actually the basis for much of civilization's infrastructures. We use about 20 billion tons of concrete every year. So this is actually far more than other materials such as timber, ceramic, glass, or metal. So therefore, despite the relatively low environmental impact of concrete compared to other materials, there is still significant space for improvement in terms of embodied carbon dioxide contents because of the huge amount of concrete we are using. Well, in order to know how to make concrete to be even greener in terms of further reduction of embodied carbon dioxide contents, let's first look at the composition of concrete. Okay, I'm sure most of you know that concrete is a composite material. Okay, this pie chart shows the main ingredients to make concrete. They are cement, coarse aggregates, fine aggregate, and water. Coarse aggregate can be gravel or crushed stone. Fine aggregate is usually sand. Some concrete may also contain supplementary cementitious materials and some other admixtures such as water-reducing admixtures. Some other materials such as fibers can also be used to achieve certain performance of the concrete. The typical proportion of these ingredients in this in a concrete mix are also given in this chart. We can see that in general, about roughly about 7 to 15% of cement is used in a typical concrete mix. Cement can react with water to form the binder to glue the aggregates together. Now, the next question is, which ingredients contributes the largest amount of carbon footprint? Where is the carbon dioxide from? Okay. Yes, I think I believe most of us would agree with me that it is actually cement. Now look at this cement carbon circle as shown here on the left, which would give us a better idea how and where we can go towards reduce the carbon dioxide emissions from concrete. Portland cement is manufactured from limestone and shale rocks that have been filed at a temperature about 1,450 degrees Celsius to form a synthetic rock called clinker. This clinker is then crushed together with a small amount of gypsum to a powder form, which is actually cement, Portland cement. Okay, when this limestone is heated, it breaks down. Okay, and it gives off carbon dioxide. This reaction is unavoidable in the manufacturing of cement clinker, and typically one ton of clinker leads to emission of 750 to about 900 kg of carbon dioxide. And among this amount of carbon dioxide, 60% actually comes from this calcium carbonate decomposition, and 40% actually comes from the fuel combustion needed for this cement production. And then, sorry, cement can hydrate when mixed with water and form hydration products, including calcium hydroxide. Calcium hydroxide, this one, can then react with the same amount of atmospheric calcium dioxide, restoring the calcium in the cement-based material to calcium carbonate again. This process would somehow offset the production emissions. However, the amount of carbon dioxide reabsorbed here can never exceed the amount on the left, because why? Because the rate of carbonation of normal concrete is very, very slow. For example, complete carbonation of a typical concrete wall would take decades. Study have, oh sorry, there is something I forgot to mention. So sorry, let me talk about that later. I'm so sorry. Study have actually revealed that people can actually reduce emissions by about 80% with known technologies if we make the most of these approaches included listed here. First, we can actually look at reducing carbon dioxide from clinker production. There has been actually a tremendous achievement in the efficiency of cement plants over recent years, and the production process is highly optimized to up to about 80% of thermodynamic limit. Of course, there are still possibly some room to improve, but not very much, and also very difficult. Of course, we can replace fossil fuels with biomass and other waste materials to operate our cement kilns, which can result in more than roughly 80% reduces in the demand for fossil fuels. Generally speaking, however, this has actually been largely done because our cement kilns are nowadays very efficient, and this is also relatively easy to implement. Of course, we can also, I will also briefly talk about innovative no-emission raw materials, including calcium alkyl claim in the webinar later shortly. Then, so this is the first approach. Then we can also think about reducing the clinker contents in cement, and this is exactly what I'm going to talk about today with using supplementary cementitious materials in concrete. But it doesn't stop us here, because we should also think about reducing the amount of cement in concrete, and this can be as simple as optimization of concrete mixture design by using good aggregate size, good aggregate grading, using appropriate admixtures and fillers, and also select a good choice of water to cementitious ratio when we do our mix design. But however, it is a bit difficult to inform so many concrete producers about these ways to save cement in concrete. Then, of course, we can actually reduce the concrete in buildings, but this is many times quite difficult to implement because the complex chain of decision making, and of course we should of course, we should also use reuse buildings. So I'd say till today, the biggest opportunity, okay, among all of this to really achieve emissions reduction fast is to reduce clinker in cement, because Portland-based cement will continue to dominate, and using supplementary cementitious materials is one of the most realistic options to reduce carbon dioxide for foreseeable future. The cement industry is working with the concrete industry to cut carbon dioxide emissions. Here we can see a roadmap to carbon neutrality has been developed to reduce carbon emissions by about 40% by the year 2030, and to attain carbon neutrality by 2050. And reducing carbon dioxide emissions by 40% by year 2030 can be obtained using currently available options such as supplementary cementitious materials and waste fuels. But attaining carbon neutrality by the year 2050, however, will likely require a carbon capture as well as non-carbon dioxide emitting fuels. Okay, on the right-hand side, we can see carbon emission reduction of is about 50% by innovative technology, including carbon capture, and it's about less than roughly 40% by reduction of the clinker to cement ratio. So both of these ways actually leads the ways in cumulative carbon dioxide emissions reduction in cement market, in cement making, in cement production. Their contribution, these two, are jointly equivalent to almost 80% of current global direct carbon dioxide emissions from the total industrial sector. Well, now we come to the next item. So what are supplementary cementitious materials? After I mentioned it many times. Well, supplementary cementitious materials are also called supplementary cementing materials. They are materials that when used in conjunction with Portland or blended cements, they can contribute to the properties of concrete through hydraulic or pozzolanic activity, or both. And the use of supplementary cementitious materials, especially pozzolanic materials, is actually as old as the art of concrete construction. Ancient Greeks and the Romans, actually they use certain finely divided siliceous materials, which when mixed with lime, they can produce strong cementing material having hydraulic properties, and such cementing materials are employed in the construction of aqueducts, arc, and bridge, and so on. And before we go to the details of supplementary cementitious materials, I'd like to briefly talk about cementization and pozzolanic reaction, which are actually the chemical reaction between cement or supplementary cementitious materials and water. Well, the mechanism of hydration of the cement as a whole is very complicated, and has actually not yet been fully understood. So far, the only approach to studying the hydration of Portland cement is to investigate the reaction mechanism of individual compounds separately. Okay, we can see the two main compounds in Portland cement are actually tricalcium silicate C3S and the dicalcium silicate C2S. The reaction of C3S and C2S with water, okay, this is water, form hydrogen products, calcium silicate hydrate, okay, CSH, and calcium hydroxide, CH. This calcium silicate hydrate, CSH, is the principal hydrogen products which makes up about 56 to 60% of the volume of hydrated paste and determine the good properties of concrete. And some supplementary cementitious materials also contain such kind of calcium contents that can react with water directly. But of course, there are also some other supplementary cementitious materials which are not able to react with water directly. Okay, but they contain glassy silica. Okay, silica here, and this silica actually do react with calcium hydroxide. Okay. Calcium hydroxide, okay, if you can still remember, is the hydrogen products from these cementitious materials. Okay, so silica can react with calcium hydroxide in the presence of water. Okay, and also the product of this reaction is also calcium silicate hydrate. Okay, it's the same or similar to the hydrogen products here from the cementitious materials. Okay. This chemical reaction here, as shown here, is called pozzolanic reaction, and such kind of supplementary cementitious materials are pozzolanic materials. So depending on their chemical and mineralogical composition and physical properties, in particular the specific surface, supplementary cementitious material generates different types of reactions when used in concrete. So based on this, they can be categorized into 3 types, okay, as shown here. So the first one is filler. So these fillers are inert supplementary cementitious materials that act as nucleation sites. They can hasten cement hydration and hardening, while also filling the pores, and thereby they can densify the microstructure of the paste. Typical examples of these fillers including limestone and say concrete powder. The second type is active non-pozzolanic additions that exhibit independent hydrolicity, okay, which means that they will be setting and hardening when mixed with water, giving rise to products similar to those resulting from the cement hydration. Typical examples of this type are ground granulated blast furnace slag, GGBS or slag, okay, and Class C fly ash. And then we can see this, the third type. The third type is active pozzolanic additions. So these are materials with a high, relatively high silica and alumina contents that in themselves, they are not hydraulic. So which means they cannot react with water directly. But when they are very finely ground, they can react with calcium hydroxide at ambient temperature in the presence of water to generate stable products such as calcium silicate hydrate, CSH. Typical examples of this type of supplementary cementitious materials including silica film, metakaolin, and Class F fly ash. This picture shows some commonly used supplementary cementitious materials from left to right. We can see they are Class C fly ash, metakaolin, or calcined clay. Next is silica film, Class F fly ash, and this is ground granulated blast furnace slag, GGBS, or you can call it slag or slag cement. And lastly, calcined shale. Of course, there are many other supplementary cementitious materials are not shown here, such as natural pozzolan, limestone, and so on. Next, I'm going to introduce some of these supplementary cementitious materials in more detail. First, let's look at GGBS slag. Okay, slag GGBS is also known as slag cement. So, in the presence of water, GGBS hydrates and sets in a manner similar to Portland cement, but this process is very slow. Okay, so how how can we get GGBS? GGBS is obtained by rapidly quenching the molten slag by using high pressure water jets in blast furnace as a byproduct from the production of iron used in steel making. This rapid quenching process transforms the molten slag to a glassy sand-like granulated material with a typical size smaller than 5 mm. Um, these are the typical chemical composition and the physical properties of GGBS. Generally, the oxides of silica, calcium, alumina, and magnesium and iron makes up more than 95% of the GGBS. And again, we can also see that the GGBS has approximately the same or greater fineness than Portland cement. Then next is fly ash. So fly ash is also a byproduct. Okay, it's a byproduct from the combustion of powdered coal as fuel in power station. Fly ash particles are mostly spherical and hollow of different dimensions. Of course, some particles of them can be irregular or solid. The shape and the surface texture of the fly ash particles have influence on the amount of water needed in the concrete mix design in order to achieve a certain workability. The particle sizes in fly ash vary from less than 1 micrometer to more than 100 micrometer, with their average size measuring less than 20 micrometer. Okay, fly ash can be, as shown here in this table, can be categorized into two types based on the types of coal burnt according to ASTM standard. So we can see class F fly ash contains less than 10% calcium oxide, and class C fly ash actually contains about 15 to 30% of calcium oxide. Okay, so they can be called as low calcium fly ash and high calcium fly ash respectively. So this class F fly ash will not react with water unless there is a source of calcium hydroxide, as we discussed before. So it is actually a true pozzolanic material. Class C fly ash, however, can be hydraulic as well as pozzolanic material, because the increased calcium contents, okay, would be incorporated into the glass contents in fly ash, which changes the structure of the glass and then makes it reactive with water directly. So this is fly ash. And so let's look at silica film. Okay, silica film is the ultra-fine non-crystalline silica produced in electric arc furnace as an industrial byproducts okay, of the production of silicon metals and ferrosilicon alloys. Sorry. Silica film is also known as condensed silica film, or sometimes microsilica. So as we can see, one of the distinction features of silica film is extremely fine and spherical nature. The mean size of silica film is 0.1 to 0.3 micrometer, which is about 100 times smaller than that of Portland cement and many other mineral admixtures such as fly ash. So the benefits of extremely fine nature include high activity resulting in high surface areas and the ability to pack between cement particles inside concrete. Of course, such fine particle sizes of silica film have also drawbacks in handling and significantly higher water demand. So usually water reducing admixture is needed to disperse silica film properly in concrete. Silica film is composed primarily of pure silica in non-crystalline form. So when produced during the manufacture of silicon metal, the silica contents is usually above 90% by mass and may even be as high as 99% sometimes. There are actually some other supplementary cementitious materials such as natural pozzolans. Natural pozzolans are produced from natural mineral deposits. Some of these materials, such as metakaolin, require heat treatment known as calcining to make them pozzolanic. Others, such as volcano ash, can be used with only minimal processing, such as drying and grinding. Well, metakaolin, also known as calcined clay, is produced by calcining purified kaolinite clay in a specific temperature range from about 650 to 800 degrees Celsius to drive off the chemically bound water in the kaolin and destroying the crystalline structure. So this actually converts the material to former's aluminosilicate. I'm sorry, aluminosilicate. Okay, there are many less common natural pozzolans such as volcano ashes and rice husk ash. Rice husk ash is produced by burning rice husk, which is actually an agricultural waste. So this can be done under a controlled temperature and atmosphere to remove the organic matter. Rice husk actually contain about 20% of silica by weight, which is actually much higher than any other crop residue. The rice husk ash contains around 80% of silica and shows excellent pozzolanic properties due to its high surface area, high amorphous nature, and compatibility with cement and concrete. Well, lastly, let's look at with the glass. Okay, glass is products of supercooling of mixture containing sand and soda ash. Some waste glass could also be easily incorporated in concrete because of its pozzolanic and cementitious nature due to the presence of large amount silicon and calcium. The properties which influence the pozzolanic behavior of waste glass and most pozzolans in general are actually fineness, so composition, and the pore size, pore solutions present for the reaction. So there are some research showing that pozzolanic property of glass are first notable at particle sizes below approximately 300 micrometer, and below 100 micrometer glass can have a pozzolanic reactivity which is greater than that of fly ash at low temperature, low percentage of cement replacement levels, and also after 90 days of curing. Glass, therefore, has the potential to acceptably function as a supplementary cementitious material. However, addition of waste glass to concrete gives rises to tricalcium silicate C3A and lowers the amount of dicalcium silicate C2S and tricalcium aluminate C3A that makes concrete resistance to sulfate attack. So proper methods must be developed to control the alkaline silica reaction or pozzolanic reaction and influence a non-destructive, non-swelling products. Okay, now let's move on to the next item. Okay, how do we use supplementary cementitious materials in concrete? Well, actually, the practice of using supplementary cementitious materials in concrete mixtures has been growing since 1970s. Supplementary cementitious materials nowadays are used in at least 60% of ready-mixed concrete, at least. Okay. Generally speaking, supplementary cementitious materials are added to cement as part of the total cementitious system. Typical practice using supplementary cementitious materials as an addition to or as a partial replacement for hydraulic cement in concrete. Fly ash, okay, is used in more than 50% of ready-mixed concrete nowadays. So in which class F fly ash is often used at a dosage of about 15 to 25% by mass of cementitious materials, and class C fly ash is used as a dosage of 15 to 40%. Some concrete may contain higher volumes of fly ash with more than 40%. The dosage varies with the reactivity of ash and the desired effects on the concrete. And then next, GGBS. GGBS commonly constitutes between 30 to 50% of the cementitious materials in the mixture when used in general purpose concrete. Some slag concretes may have a slag component of say 70% or more of the cementitious materials for applications such as mass concrete and marine environments. Okay. And then silica film. Okay, silica film is typically used in amounts between 5 to 10% by mass of the total cementitious materials. It is used in applications where a high degree of impermeability is needed, and also in high strength, high performance concrete. Metakaolin is also used in applications where very low permeability or very high strength is required. So in such kind of applications, metakaolin is used more as an additive to the concrete rather than a replacement of cement. And the typical additions are around 10%, okay, of the cement mass. And then the performance of concrete using rice husk ash is dependent on many factors, including the level of Portland cement replacement, the particle size of rice husk ash, and so on. So for successfully strength development, around 10 to 25% replacement of ordinary Portland cement with rice husk ash is recommended. Then grass powder. Grass powder can be used to replace Portland cement, typically at 10 to 30 replacement level by weight. While concrete is in its plastic phase, glass powder will increase its workability, so it actually requires less energy, cost, and time to place and to consolidate the concrete. But while the concrete is in its hardened phase, concrete containing glass powder actually exhibits better strength, free and zone resistance, and sulfate resistance. Okay, on the right-hand side, actually, I also gathered some data from a colleague of mine who's working in Sika Limited, Vietnam. According to the information, the trend of using supplementary cementitious materials in Vietnam actually began about 2 years ago, and the most typical supplementary cementitious material in use are fly ash and GGBS. When fly ash is used alone, okay, the typical replacement level is 10 to 30%. A few customers use 40% for board pile, and some special customers use 50%, and but only used in ready mixed concrete. GGBS replacement level is about 30% when used alone for span piles. Some special customers use GGBS alone as high as 50%. Of course, there are also some applications of ready mixed concrete using fly ash plus GGBS at around 50%, with fly ash being 30%. So we can see now there are some applications with more than one types of supplementary cementitious materials, right? So this actually brings us to another concept, which is ternary, or sometimes even quaternity system when using supplementary cementitious materials. Okay. Sorry. Traditionally, supplementary cementitious materials were used in concrete individually with Portland cement. However, there are benefits in using more than one supplementary cementitious materials in combination with Portland cement to produce concrete mixtures. So, for example, ternary blends containing Portland cement, okay, plus 1 to 2 supplementary cementitious materials are often used where special properties are required. And we can see quaternity blends consisting of Portland cement and 1, 2, 3 supplementary cementitious have also been used actually. So there can be a pronounced synergy in combining different supplementary cementitious materials, either fly ash, slag cement, or silica fume. For example, silica fume can offset the increased water demand of fly ash can offset the increased water demand of silica fume, and Class F fly ash or GGBS actually compensates for the high heat released from the blended cement with silica fume, and also increase the long-term strength development of silica fume concrete. Or the other way around, okay, silica fume, okay, actually can compensate for low early strength of concrete using fly ash or GGBS. Silica fume, okay, silica fume also can reduce the normally high level of Class C fly ash or GGBS required for sulfate resistance and alkali silica reaction prevention. So here are a couple of examples of projects using ternary mixtures. So in the first projects for a bridge deck, about 30% of GGBS and 15% of Class F fly ash were used in addition to the ordinary Portland cement. Okay. But in the second and the third projects, it seems that only one supplementary cementitious materials, here class C fly ash and here class F fly ash, was used in addition to certain types of cement. Okay, as we can see here. Okay, well, this actually brings us to another approach how we can actually use supplementary cementitious materials in concrete, which is actually blended cement. Okay, blended cements, which already contain pozzolans or slag, are designed to be used with or without additional supplementary cementitious materials. Blended cement is produced by intimately and uniformly intergrinding or blending two or more types of fine materials. So the primary materials are, of course, Portland cement, slag, fly ash, silica film, calcine, clay, and some many other pozzolans or hydrated lime and pre-blended combination of these materials. Blended materials must conform to the requirement of relevant standards in different countries. So for example, Australian standards, so this is EU standard, this is ASTM standards. Blended cements are used in all aspects of concrete construction in the same manner as Portland cement, and the blended cements can be used as soil cementitious materials in concrete, or they can be used in combination with other supplementary cementitious materials added at the concrete plant. Blended cement has been done for so many decades now. So this chart on the left shows the figures for the substitution rates from the global cement and Global Cement and the Concrete Association. We can see that the overall level of substitution is actually below 25%. Okay, apart from gypsum, the most used materials is actually limestone, slag, fly ash, pozzolans, and some other materials. Okay, this one. And if we read this chart carefully, we can see the past decades, okay, actually did not see much progress in the level of substitution, most probably due to the storage of these substitution materials, which I will be briefly discuss later on. Okay, nevertheless, the majority of the cement today, okay, around the world are in fact blended cements. So we can see, as we can see here, so roughly, probably roughly 3/4 of cement sold in the year 2010 are actually blended cements, okay, as indicated by the figure here on the right. Now let's move on to the next item. So what are the benefits of using supplementary cementitious materials, okay, in concrete? Well, let's first look at the economic benefits. Okay, as mentioned early on, many supplementary cementitious materials are actually byproducts in other industrial processes. So this indicates that supplementary cementitious materials could be potentially much cheaper because many of them are industrial wastes. Indeed, most supplementary cementitious materials are much cheaper than Portland cement. For example, nowadays in Vietnam market, okay, concrete costs about 1,600 to 1,800 Vietnamese dong per kg, which is about 0.096 to 0.11 Australian dollar. Okay, whereas fly ash, okay, only costs about 400 to 500 Vietnamese dong per kg, which is about 0.024 to 0.003 Australian dollar per kg. So it's only roughly 1/4, okay, of the price for cement. Okay, slag. Okay, slag costs about 1,000 Vietnamese dong, which is about 0.06 Australian dollar, and it's just about half of the price for cement. Okay, then in China, okay, China, who produces the most cement globally by a large margin, okay, in year 2021, last year, the price of cement had risen to 0.65 RMB per kg, which is about 0.13 Australian dollar, while that of silica fume, okay, had fallen to 0.4 RMB per kg, which equals to 0.083 Australian dollar per kg in some areas. So which is also, we can see, is also much cheaper than cement sales, right? So the price of supplementary cementitious materials is so much cheaper than cement. Using supplementary cementitious materials in concrete can greatly reduce the material cost of producing concrete. The supplementary cementitious market is primarily driven by the increase in construction activities across the globe. Supplementary cementitious market size was valued as about 22 million US dollar in year 2020, and is projected to reach about 34,000 million US dollar, okay, by 2028. So it grows actually at a compound annual growth rate of 6.21% from 2021 to 2028. Currently, fly ash segments accounts for the largest share in the supplementary cementitious materials market because it's really cost effective. Now, at this point, when we are saying supplementary cementitious materials are much cheaper, so does it mean that we have to compromise the quality of concrete if we want to use supplementary cementitious materials? Well, this is actually not true. In fact, surprisingly, using supplementary cementitious materials most of the time means that we can get a concrete of better quality and better performance. Well, it has been demonstrated that the best supplementary cementitious materials in optimum proportions mixed with Portland cement improves many qualities of concrete. For example, in terms of the fresh properties of concrete, we can see that actually many of the supplementary cementitious materials can reduce the water demand, okay, and increase the workability and reduce the bleeding and the segregation. Okay, the effect of silica fume and metal cowling on these few fresh properties are different because they are because of their large particle surface area coming from very fine particles. So chemical admixtures such as superplasticizer can be used to adjust these fresh properties when silica fume or metal cowling is used. And then we can see that the use of supplementary cementitious materials will generally retard the setting time of concrete. So sometimes accelerating admixtures can be used to decrease the setting time, especially during cold weather. Okay, and supplementary cementitious materials also generally, okay, as we can see here, requires an increase in the amount of L-engineering admixture needed due to the increase in the fineness of the cementitious materials contents. And lastly, we can see incorporating supplementary cementitious materials in concrete can also many times reduce the hydration heat of fresh concrete, and it's good for mass concrete structure. Then when it comes to hardened properties, we can see that in general, all supplementary cementitious material contribute to the long-term performance of concrete, including increased long-term strength, reduced reduced permeability and absorption, okay, higher corrosion resistance, and lower alkaline silica reactivity, and better sulfate resistance, and so on. Okay, supplementary cementitious materials, they can modify the microstructure of the hydrated matrix quite significantly. The increased fraction of calcium silicate hydrate (CSH) leads to a more homogeneous microstructure, particularly when highly reactive, finely divided supplementary cementitious materials are used. Adding supplementary cementitious materials will reduce the overall porosity and the pore sizes of the hardened concrete. But then if we look at early strengths, so just now we talked about long-term strengths. If we look at early strengths, okay, early strengths of concrete containing supplementary cementitious materials can be lower than the strengths of concrete using Portland cement alone, which could be partially attributed to the lower hydration rate of the supplementary cementitious materials. But overall, we can see that the use of supplementary cementitious materials results in stronger and long-lasting concrete. Well, of course, one main reason why we use supplementary cementitious materials in concrete is the environmental benefits. It is not only about using industrial waste to relieve some pressure on landfill demands, but more importantly, substantial reduction of carbon dioxide emission can be achieved by replacing part of cement used in concrete by these supplementary cementitious materials. The carbon dioxide reduction is proportional, okay, to the percent of replacement of cement. In general, for every ton of clinker replaced by supplementary cementitious materials, carbon dioxide emissions are reduced by approximately 0.8 ton. Okay, and as we can see from the figure on the left, that with the supplementary cementitious materials replacement ratio of about 50 to 60%, the embodied carbon dioxide reduction, okay, from compared to OPC, okay, the reduction, okay, ranged from about 30% to about almost 50%, okay, which is very, very significant. Okay, so these are mixtures with supplementary cementitious materials, and this is OPC, ordinary Portland cement. Okay, another study on the carbon footprint of different types of cement in EN standards also indicates substantial carbon dioxide reduction of blended cement. Okay, so these are blended cements, okay, over ordinary cement. So this is ordinary cement. Okay, so we can see that is a substantial reduction. Okay, well, in this table, I'd like to point out, okay, there is another type of cement called a Portland limestone cement. Okay, so this one, okay, it actually exhibits about 10% of carbon dioxide reduction, okay, over Portland cement. So this actually will brings us to the last agenda item of this webinar, okay, which is about the new trends in green concrete. Okay, Okay, the first one I'd like to share with you is actually the Portland limestone cement that we saw just now. Okay, Portland limestone cement (PLC) is actually not something new. It was first developed in Europe in the 1960s, and the first Portland limestone cement application for paving took place in US in year 2007, and is now used in many countries as the preferred cement products due to the fact that it actually reduces the carbon footprint of a concrete mix significantly. Portland limestone cement, okay, this one looks quite similar with Portland cement. Okay, the difference between these two is that in addition to the clinker and the gypsum, okay, used for Portland cement, so this is Portland cement, okay, we add limestone, okay, when grinding this clinker and the gypsum to make Portland limestone cement. Okay, so this Portland limestone cement is essentially a type of blended cement. Standards in different countries specify different percentages of limestones can be added in Portland limestone cement. Some of them are listed here. Typically, it's between 5 to 15% limestone. The product itself performs the same as standard concrete, but it comes with great benefits. And Portland limestone cement are in common use around the world, and it is actually a proven solution for reducing carbon dioxide of cement without sacrificing the performance. As demonstrated in the table we saw a couple of minutes ago, typically Portland limestone cement can reduce carbon footprint by 10%. With Portland limestone cement, similar percentages of supplementary cementitious materials can be used in concrete mixes, while also replacing up to 15% of Portland cement with limestone. So this results in a further carbon dioxide reduction associated with the production of Portland cement clinker. When combined with a high percentage of supplementary cementitious materials, say 40 or 50%, the effective reduction in the carbon dioxide footprint of concrete is highly significant. Okay? For many applications, Portland limestone cement can improve or can actually provide equivalent or sometimes even better performance with reduced environmental impacts. For example, this figure on the right, this figure shows the strength for concrete made with water to cementitious ratio about 0.4 for specimens without any supplementary cementitious materials, and with about 35% of slag, or with 20% of fly ash at different ages. So this is 1 day, 7 day, 28 day, and 56 days. The light blue columns are for a control mix using Portland cement, and the yellow ones, the yellow columns, are actually for another mix using Portland limestone cement. So we can see that the early age and the later age of concrete strengths are actually similar when made with either Portland cement or Portland limestone cement, right? So this is very impressive. Okay. Also, supplementary cementitious materials, we can see. Okay, so the last two columns in each of these different charts. Okay, so supplementary cementitious materials, okay, actually can we can see that the supplementary cementitious material actually tends to have a lower, okay, early age strength, okay, but later on they will have increased, okay. So as we can see here, okay, a higher long-term strength, okay, for both concrete with Portland cement or Portland limestone cement. So this trend, okay, early strength and the long-term strength for concrete using supplementary cementitious material is similar to what we discussed early on, okay. Overall, Portland limestone cement gives us, okay, say architects, engineers, producers, and designers a greener way to execute any structure, paving or geotechnic projects with virtually no modifications to mix design or placing procedure. Okay, nowadays, okay, there are, I'd say, there are still some barriers preventing more widely application of Portland limestone cement, such as lack of education and training, and sometimes there are also supply chain restraints and so on. In addition to the Portland limestone cement, I would like to also briefly talk about another emerging trend, which is limestone calcined clay cement, which is LC3. Nowadays, limestone, GGBS, and fly ash constitutes the overwhelming majority of mineral additions. However, there is actually limited potential for further carbon dioxide reduction by clinker substitutes because of the limited supplies of slag and fly ash. So we can see this figure. Okay, we can see from this figure. This figure shows the estimated availability of possible supplementary cementitious materials and fillers. We can see that the most commonly used supplementary cementitious materials like fly ash, slag are already or almost fully used and cannot be scaled up for the use in cement. And furthermore, with increased focus on sustainability, more and more coal power and steel production plants are expected to be closed. So this will further cut the supply of these materials as a supplementary cementitious material. And the only material largely available and in sufficient quantity are clays. Okay, the wide use of calcined clays can meet the growing demand for cement alternative materials. The production of calcined clays involves similar requirements to ordinary Portland cement and approximate cost of investment. We can see the scarcity of common supplementary cementitious materials has actually promoted the use of calcined clays as an alternative. Okay, calcined clays have been used for decades as pozzolans. Okay, but recent developments have shown that clays containing at least 40% of kaolinite as main clay mineral can be highly reactive if properly thermally activated. So this is exactly LC3. So LC3 is a new type of cement made with using limestone and low-grade clays, which are available in abundant quantities. Okay, and it's also cost-effective and does not require capital-intensive modification to the existing cement plants. So this is a typical composition of LC3. So when limestone, okay, this is limestone, is added into cement. So cement is a gypsum, basically ordinary Portland cement is gypsum plus clinker. So when limestone is added into the cement and the calcined clay blend, the synergy, okay, between these two supplementary cementitious material, limestone and the calcined clay, okay, so this synergy between them would enable higher clinker substitution with an improved performance both in terms of mechanical properties and durability. Okay, and also low energy is consumed in calcination at a lower temperature of clay. So for clay, we need temperature of about 750 to roughly 850 degrees Celsius. But for clinker, if you can still remember, the temperature is actually 1,450 degrees Celsius. So, we only need lower temperature for clay than that for clinker. So as a result, LC3 can reduce carbon dioxide emission by up to 40%. And most importantly, performance of LC3 is equivalent and many times better than that of ordinary Portland cement. So as we can see from this figure, LC3, which is actually the green color ones, okay, reaches slightly lower values than OPC, okay, at 1 day. Okay, so OPC is actually the gray color one. Okay, so at 1 day, the strength of LC3 is lower than OPC, but it catches up at about age of 7 days. Okay, and also we can see that the strength of LC3 actually exceeds OPC. Okay, after 7 days, so we can see a higher strength of LC3 than OPC. Okay, as shown here. Okay, and moreover, so if we compare the performance of LC3 with some other concrete using supplementary cementitious materials like slag and fly ash, so these orange and red color ones, we can see that LC3 actually shows higher early strength than other blended cements, right? So this is the strength behavior. In addition, LC3 has higher resistance against chloride ingress compared to ordinary Portland cement, and compared to ordinary Portland cement with 30% of fly ash. LT3 also performs well in tests for sulfate resistance. And there is also a significant improvement of alkali silica reaction mitigation compared to ordinary Portland cement. Reasons for this improved performance are the additional chemical reactions compared to ordinary Portland cement, including the pozzolanic reactions of calcined clay and limestone reactions, and most importantly, the synergetic reaction of the calcined clay and the limestone. Because the alumina contents of calcined clay enhances the limestone reactions. Some research also indicates that LC3 production cost is up to 25% lower compared to ordinary Portland cement production. LC3 could be one of the best solutions to our goals for greener and better concrete. Well, so these are all from me today. Thank you very much for your attention.
Thank you very much, Shasha. I'll just reshare the slides. Thanks again, Dr. Shasha, for that a very informative presentation. Before we wrap up the webinar, I'd just like to go over a few upcoming civil and structural engineering courses that we offer. So in February, we have a few starting. So our Advanced Diploma of Civil and Structural Engineering is starting on the 7th of February. We have our Bachelor of Science in Civil and Structural Engineering and our undergraduate certificate starting on the 13th of February. And we also, if you're interested in one of our postgraduate programs, like our Masters or our graduate diploma, or we have some graduate certificates in civil engineering as well, we those will be starting on the 26th of June next year. Now, all these courses I've mentioned are all of our online modes. But if you are interested in studying on campus in Australia, we do offer bachelor's and master's degrees on campus in Australia. And I would recommend, if you would like to have a look at our full course schedule, to go to our schedule page on our website. The link is down below there. I can put it in the chat box if anyone's interested. And we don't have any upcoming webinars at this stage, but we're planning a few for January at the moment, and we hope to have those up well before Christmas. So yeah, stay tuned for 2023, and you can check our events page whenever you would like to see if there's any upcoming webinars there that you can register for. You can also see all of our past webinars on that page as well. Now, as promised, we also provide the digital certificate of attendance for these technical webinars. So if you have your if you're on a desktop or a laptop and you've got your phone there, you can scan the QR code on the screen, or I'll put the link in the chat box. That link that I've just put in the chat box, that'll send you to a short survey about this webinar. And once you fill that short survey, you'll be able to receive your certificate of attendance, and we will send these out within the next 24 hours. So look out for those, and they may go to your junk email folder. So check your junk email folder as well. So just refer to the link that I've sent in the chat box. You don't need to complete it now if you don't want to, but you can complete it after the session if you would like. And that pretty much concludes the webinar for today. We'll have a short live Q&A. If anyone has any questions, just feel free to put them in the chat box. But I'll skip to the last slide so that if anyone needs to go, thank you very much for coming today. We really appreciate it. All of our contact details are on the screen if you need it. You can reach me directly at webinars@eit.edu.au if you would like to send me an email. But otherwise, as I said, please put any questions in the chat box if you have any. If you have any for Dr. Shasha or myself, we'll be happy to answer any questions for you.
Hi, Randy. I can see that there was a question about how about use hemp as supplementary cementitious materials. So thank you, Jim. Thank you for your question. So hemp is also some agricultural products, I'd say. So there are some studies using hemp as supplementary cementitious materials, but it really depends on the performance and also most importantly, the availability of these materials in a large quantity. So because cement is we need to use a lot of cement, so it depends on how easily we can access those supplementary cementitious materials such as hemp. I'd say it's not so far not widely used, but there is potential. Okay, thank you.
Thanks, Shasha. Yeah, I will just provide the CITIGO attendance link again. I'll just pop that in the chat box. If anyone has any questions about our civil engineering courses as well, please feel free to ask. We'll try and answer them as best we can. But otherwise, please feel free to reach out to us. You can go to our website and you can speak to one of our course advisors. If you'd like to schedule a call with one of them or speak to them on live chat, they're more than happy to help. I think there's just a question come through there for you, Shasha, from Owen.
Thank you, Rani, and thank you, Haran. What is the best combination mineral admixtures to design high-strength concrete? I'd say there are quite a lot of opportunities. So you can look at many studies. So many of them claim this is the best high-strength concrete, but generally speaking, okay, for high-strength concrete, high-performance concrete, typically, okay, typically there are silica fume. I tell you, okay, silica fume is most of the time needed when people producing high strength concrete because of its extremely fine particles. It is very fine with high surface area, so it can be a very good filler, I'd say, okay, in between the cement hydration products and improve the cement the microstructure of cement hydration product CSH significantly. So when you see high strength concrete, typically there is silica fume, but silica fume itself cannot make the job perfectly. So many times we need to add other supplementary cementitious materials. For example, as we discussed, we may introduce fly ash, add fly ash into it to modifying the mixture. Okay, so it's not only about the reactions between different supplementary materials and the cement, but it is also there is another criteria, or I'd say is actually the particle size distribution. So if we can design the mixed proportion properly so that we have a nice distribution of the sizes, so different particles, components inside the concrete mix can pack properly, okay, reasonably, then we are going to make good concrete, okay, better concrete. So typically, I'd say for high performance concrete, there will be many ingredients, okay, including silica fume, including perhaps GGBS or fly ash, and that's only for high strength. And therefore, nowadays, people are talking a lot about high performance concrete and ultra high performance concrete. So for this type of concrete, typically we have to add fibers, okay, to achieve high performance and even higher strength. So there are many options. So I cannot simply say which is the best. Many of them can achieve the targets you want, the target strength you want. So there is another question: what are the effects of admixtures on green concrete? As we discussed during the webinar, so the most in terms of the green concrete or the environmental aspect, okay, the most significant reason is that supplementary cementitious materials does not produce as much as carbon dioxide as cement. So when we replace part of the cement needed for concrete using supplementary cementitious materials, we can cut down carbon dioxide released by the concrete. So this is the main reason, okay, I'd say, or the main effect of admixture on green concrete.
Thanks, Shasha. Doesn't appear there's any more questions at this stage, but as I said, if anyone wants to reach us, you can do so through our website, or you can send me an email directly. But thank you all very much for attending today. We really appreciate it, and we hope you have a great rest of the year, and hopefully a nice break as well. So yeah, thanks everyone, and yeah, have a great rest of the year. Thanks again, Dr. Shasha.
Thank you everyone. Thank you for coming. Thank you very much. Bye bye.
Thank you.